All right, everybody, welcome to Math with Grace. Today we're going to be working through Algebra 2, Book 10, Lessons 6 through 10. Lesson 6 begins on page 19, and it's titled Summation Notation. Now, I've mentioned this symbol before, and we didn't actually use it. The book used to use an S, right? And a lot of those formulas are going to come up again, but for now, let's take a look at this summation notation. So, summation notation is a short way to indicate what needs to be added. The Greek letter sigma indicates the sum of a series. The expression following the sigma is the expression that needs to be added. So in this case, 6k minus 3. The numbers, they aren't here, but they are here. Above and below the sigma are the limits of the series, okay? The lower number contains the index of summation, the variable that you're using, k, and indicates the starting point of the series. So here, k equals 1. So we're going to start summing these together, adding these together, where k equals 1. Right now there's a question mark. The next one, it is filled in. The number above the sigma represents as far as the calculation should go. So we're going to go until k equals 5. They don't put the k, it's just a 5, but that's what that means. So we're going to go from k equals 1 to k equals 5. In the explicit formula, 6k minus 3. To calculate the series manually, you evaluate the formula for each index number from the lower to the upper limit and add the results. So they've done that here. 6 times 1 minus 3 is 3. 6 times 2 minus 3 is 9. 6 times 3 minus 3 is 15. 6 times 4 minus 3 is 21. 6 times 5 minus 3 is 27. The total is 75. So that's the summation of that data, right? Now, here is a summary. If the explicit formula represents an arithmetic series, we can calculate the first and the last terms using the formula for the sum of n terms in arithmetic series. Here is that formula. It's from Unit 8, page 6. Now, down here it says, all arithmetic series formulas are single variable linear expressions, such as this, 6k minus 3, right? Let's turn the page. At the top of page 20, it says the summary is continuing, and we're going to keep reading it. If the explicit formula represents a geometric series, determine the first term and r, then use the formula for the sum of n terms in a geometric series. That's why I said these are summation notation, except they used an S, which is interesting. But I don't know why they just didn't teach it to us this way in the first place. But we've done these problems before, okay? We actually have done them before. It's just now they're writing them in a different way. So it says, then use the formula for the sum of n terms in a geometric series. And so here is the sum of n terms. Unit 8, page 30, and then it also says, or the formula for a convergent series, which is here, which is on page 50. All geometric series formulas are a ratio raised to a power that is 1 less than the index, which is like example 2 down here, right? Here's a ratio, a fraction, raised to a power, which is 1 less than the index. And then it says, if a series is neither arithmetic nor geometric, calculate the sum manually as illustrated in the example we just did. So let's take a look at this example number 1. What was the last example called? Oh, it didn't have a number. All right, example 1. The summation of 6k minus 3 from k equals 1 to 15. That's how I would read that. The book doesn't really illustrate it too much, but that's how I would read that, okay? It says this formula is a linear formula indicating that the series is arithmetic. Now, the book has a few errors, but nothing we can't correct, right? It says calculate a sub 1 and a sub 15. Right? We're going to calculate where we're starting, and we're going to calculate where we finish so that we can use this formula that we've already used. We've already learned, okay? Now, a sub 1 is going to be 6 times 1 minus 3. So they just have the wrong formula plugged in here, which is 3. And 6 times 15 minus 3, which is 87, okay? We just calculated those by substituting the values into this formula, all right? Or into this equation, I should say. And then it says, figure the sum with the formula for the sum of n terms in arithmetic series, okay? Now, the arithmetic series formula I wrote on the other page, but they have it here. So S sub n equals n over 2 times a sub 1 plus a sub n. Now we have to substitute in the actual values. Again, the book, it just has a miscalculation. And when we solve, we get 675. Okay? So the summation of this summation, although this should say 6k minus 3, I guess I missed that part in my correction here. Let me find my pen. 6k minus 3 is 675. Now, the summation for 5k plus 3 might be 645, but that's not what they started with, so I don't know. I didn't check that math. All right? Okay, so piece of cake. We've already used these formulas, so this should be pretty comfortable. Evaluate the summation of 5 times 1/2 raised to the power of k minus 1 from 1 to infinity. All right, so now we're looking at this formula, right? It's an infinite series. So is my absolute value of r less than 1? It says here that we need to determine our r and calculate a sub 1. Our r, goodness, say that 10 times fast, is 1/2. That's what that's the ratio that we're raising to the power. So our r is less than 1, so we can use this formula. And then we need to calculate our a sub 1. And our a sub 1, simply we substitute a 1 into here for k, into the equation. Okay, so we have 5 times the quantity 1/2 raised to the power of 1 minus 1, or 0. Anything raised to the 0 power is 1, so 5 is our a sub 1. All right, now that we have our a sub 1 and our ratio, our r, okay, we can use this formula for the s sub infinity, or the summation to infinity, right? It's going to be a sub 1 over the quantity 1 minus r, or a sub 1, 5 over 1/2, because 1 minus 1/2 is 1/2, which is actually 5 times 2, right? We can't divide by a fraction, so we multiply by the reciprocal. So s of infinity, or our summation of infinity, is 10. And again, they just have it, they just put the same thing again. It was just a mistake. So the summation of 5 times 1/2 raised to the k minus 1 power from 1 to infinity is 10. All right. Okay, last example, top of page 21. We have evaluate the summation of the quantity k squared minus 2 from k equals 1 to k equals 7. It says this formula is neither arithmetic nor geometric, okay, because we have, it looks like arithmetic, but we have a k squared. And remember, arithmetic is just a linear term, which is an exponent to the power of 1. So we have to evaluate the formula at each point. So it's just from 1 to 7, but it is that much math. So 1 squared minus 1 is -1. 2 squared is 4, minus 2 is 2. 3 squared is 9, minus 2 is 7. 4 squared, 16, minus 2 is 14. 5 squared is 25, minus 2 is 23. 6 squared is 36, minus 2 is 34. 7 squared is 49, minus 2 is 47. they've added them up and got 126. So the summation is equal to 126. Okay, so sometimes, even though we've got all these formulas, we're still going to be doing the math because. All right, so let's take a look at these problems together. So we are in Algebra 2, Book 10, Lesson 6, page 21. I've got the different formulas written up here, and the instructions read, evaluate the series if possible. Okay, so let's take a look at number 1. We are looking at the summation of 7k plus 5 from k equals 1 to k equals 6. All right, that's what we're looking at. That is not a linear, but not a geometric, but an algebraic. That's an algebraic expression, which is this formula here. And so let's do it up, right? So we need to know a sub 1 and a sub n. So obviously my a sub 1 is 1, because that's where we're at. Well, no, my a sub 1 is not 1, but my a sub 1 is where we're starting. And so we substitute a 1 into the formula. So we make our k equal to 1. So my a sub 1 is going to be 7 plus 5, which is 12. All right. My a sub 6, which is the end of our series that we're trying to sum up, right, is going to be 7 times 6 plus 5. Now 7 times 6 is 42 plus 5 is 47. So we now have the a sub 1 and the a sub 6 that we needed. So we can do this formula. So the sum of this series from 1 to 6, because that's what we're looking for, so s sub 6, you could probably just write s, is going to be equal to n, which is again my 6, over 2 times the quantity 12 plus 47. This reduces to a 3, all right? 12 plus 47 that's 59. So 3 times 59 is where we're at here, which is 177. So the summation of 7k plus 5 from k equals 1 to 6 is 177. All right. We've done these formulas back in Book 8. If you aren't sure about what they mean, what the different parts mean, go back and review that. Otherwise, let's keep going forward here. For number 2, we have the summation of 1 over k from k equals 1 to k equals 4. That's what we're looking at. Now, this is neither a algebraic or a geometric, because for it to be a geometric, we would have to have a ratio here, but that's where our variable is, so that's not going to work. So we need to do this manually. So we're going to add 1 over 1, because that's what k, we're going to substitute k for 1, plus 1 over 2, plus 1 over 3, plus 1 over 4. Okay, that's what we're adding. Our lowest common denominator is going to need to be a 12. So I have 12 over 12 plus 2 needs to be multiplied by 6. So we're going to multiply the numerator by 6. So 6 over 12 plus 4 over 12 plus 3 over 12. Okay. This is 10, 22, 25, 25 twelfths this is. Now you could change that to an improper fraction. What is that? 2 and 1/12 this is. But 25 twelfths is fine with me. So that one we had to do manually. Luckily, we only had to go to 4, so we were able to accomplish that. For number 3, we are looking for the summation of 3 times 1/2 raised to the power of k minus 1, where k equals 1 to infinity. So we're looking at an infinite geometric series. The absolute value of r, which is 1/2, is less than 1, so we can use the infinite series formula. We just need to know what our a sub 1 is. So to calculate our a sub 1, we're going to substitute 1 in for k. So we're going to have 3 times 1/2 to the power of 1 minus 1, or 1/2 to the 0 power, which becomes a 1, and therefore 3 times 1 is 1. So my a sub 1 is 3. So my s to infinity, and you know how much I suck at drawing those, so I'm not going to, is going to be 3 over 1 minus the ratio, which is 1/2, right? Or 3 over 1/2, which is the same as 3 times 2, right? We have to multiply by the reciprocal. So the answer is 6. Okay? Number 4. We have the summation of the quantity k squared minus 5 from k equals 1 to 6. Now, k squared minus 5 is not an arithmetic series or an algebra, or it's not a geometric series as well. And therefore, we have to do it out manually, just like we did here for number 2. All right? So we're going to be putting in our value for and figuring out our value for every step of k. So for the first one, we have 1 quantity squared minus 5. Okay, well, 1 squared minus 5 is a negative 4. Then we have plus 2 squared minus 5. Remember, these are like individual things. So 2 squared is 4, minus 5 is a negative 1. And then we have 3 squared minus 5. 3 squared is 9, minus 5 is 4. And we have 4 squared, I'm going to run out of room, minus 5. 4 squared minus 5, or 4 squared is 16, minus 5 is 11. And then we have 5 squared minus 5. I'm going to run out of space. 5 squared is 25, minus 5 is 20. And then I'm just going to write it up here, I guess. 6 squared minus 5, because remember, that's as far as we're going. 6 squared is 36, minus 5 is 31. Now this plus 4 and this minus 4, they cancel each other out. 20 plus 31 is 51. 62 minus 1, 61. Now, you do not have to rewrite all this equals 61. 61 is a great answer. Okay? So for this one, we had to do each part manually. Then add them together, because that's what a summation is, right? We're summing it up, adding every piece. All right, we've got 2 more to do. Let's take a look at those. Looking at number 5, we have the summation of k minus 1 from k equals 1 to infinity. Now, this is an algebraic expression, right? We have a single variable raised to the power of 1, but it's to infinity, which tells me that this number will get infinitely large forever and ever, amen. So you can't actually solve for that. It's just going to go on and on. That's not a solvable problem, okay? They're not going to converge to one number like this one did, number 3, right? It's just going to get infinitely large forever and ever, amen. So we can't solve number 5, all right? But let's take a look at number 6. For number 6, we have the summation of 5 times 2 raised to the power of k minus 1 from k equals 1 to 10. Now, this one we can solve because we have our ratio, which is 2. We have it raised to the power of k minus 1, which is what we need to start this, okay? And therefore, we can solve this. And we would use, this is a geometric series, so we will use this formula here, which we haven't used yet. So we get to use that one finally. But we need to know our a sub 1 to follow that through. So let's calculate our a sub 1. Is going to be 5 times 2 raised to the power of 1 minus 1. Again, 2 raised to the 0 power is 1, so our a sub 1 is 5. So putting this information into this formula, we get s to n, the n power, which is this case is 10, is going to equal a sub 1, which is 5, times 1 minus 2 to the 10th power. Remember, our n is 10 this time. Okay, all over 1 minus r, which is 2. Okay, so our s sub 10 is going to be equal to 5 times a very large number. We'll calculate that on our calculator. I just want to get up these other parts, so 1 minus 2 to the 10th power over a negative 1. All right, so this is a lot of calculator work, so we're going to jump on here with our calculator. So I'm starting here at 1 minus 2 to the 10th power, okay? So I'm going to say 1 minus 2 raised to the power of, is that just this one? Yep, 10. Close the parentheses. Make sure you're closing your parentheses. I'm going to hit equals. I'm going to multiply that by 5. So negative 5,100, 105 over negative 1 gives me a positive 5,115. Okay, so the summation, of 5 times 2 raised to the power of k minus 1 from k equals 1 to 10 is 5,115. Okay, so we got to use that formula at least once. So remember, this formula here is for the arithmetic series. This formula here is a geometric. This one's geometric as well, but it's for the infinity. But remember, the absolute value of r has to be less than 1. Okay? Again, these are all from book 8, so if you need to go back and review, do not hesitate in doing that. If you have a question, do not hesitate to contact me. All right? Otherwise, that's it for this lesson. We're just reapplying formulas we've already used in a different notation. They should have just notated it like this in the first place, if you ask me, but that's neither here nor there right now. Go ahead and finish the rest of lesson 6 and meet me back here for lesson 7. Lesson 7 begins on page 23, and it's titled Bacterial Growth and Radioactive Decay, Part 2. We got a lot of Part 2s in this book. It's so exciting. All right, so when the unknown variable of a growth/decay problem is the exponent, it can be solved using the properties of logarithms. So what does that look like? Let's take a look at example 1. A radioactive sample has a half-life of 8 years. So we already know our G is a half-life. The period is 8 years, okay? How long will it be? So now we're saying we don't know the time. How long will it be means I don't know what the time is, okay? Until a 500 gram sample, so my A sub 0 is 500, is reduced to 400 grams. That means my A, which is just the ending result, is 400. This is the data that I was given in this story problem. Let's put it into the formula, and I rewrote the formula here, even though they have it here, but remember it's from Unit 9, it's on page 28. So now we're going to substitute the information that we know. We know our A is 400. We know our A sub O is 500. We know our half growth is 1/2, right? The half-life. And then for the exponent here, we don't have the T, but we do know the P, which is 8. So now that we've substituted in everything we know, we're going to solve the little bits that we can. Our purpose at this point is to get this ratio raised to a power by itself. We want to get that alone, right? It's being multiplied by 500, so they divided both sides by 500. So we have 0.8 is equal to 1/2 raised to the power of t over 8. Now, remember, this is where the logarithm properties come in handy. If we change these both to log, okay, if we throw the log out front, then this exponent pops into the front, remember? So that's what they've done here. They've brought that one to the front. Now, this is the same. Okay, so not the same. They are going to divide both sides by the log of 1/2. Okay, that's where we're at, minus this 8. We'll get to that in a minute, right? They've divided both sides by the log of 1/2. They just changed this to a decimal since we have a decimal over there. It makes sense. Now, this 8 is because 8 is in the denominator. To cancel it, we have to multiply both sides by 8. That's why the 8 ends up here in the numerator, being multiplied, okay? And so that's the formula for solving t. And you're going to use your calculator and see that t is approximately, because you have to round. Once you round, it's not an actual equals, right? Approximately 2.6 years, all right? Let's look at the next example. We just have to be vigilant with our math, okay? Again, formula we've used. We just need to be vigilant with our math. Example 2, a 500 milligram dose of the antibiotic, nobody cares what it is, my A sub O is 500. After 180 minutes, so that's my time, only 65 milligrams remains. So now my A is equal to 65. What is the half-life period? Half-life means we know our G now. And the half-life period, that's what we're looking for. We don't have our P this time. So let's substitute what we know. We know my A is 65. We know the A sub 0 is 500. We're dealing with the half-life, so we have 1/2. Raised to the power of 180, because we're talking about minutes, divided by P. So now we're doing the same process, okay? We're dividing both sides by 500. We're changing them over to a log. We're booping our exponent here into the front of the log, right? We're dividing both sides. Well, this one's a little bit different. So I personally, since my P is in the denominator, would multiply both sides by P. Okay. And then you have to divide, this time, by the log of 1.3. So you end up with 180 log 1/2 divided by the log of 0.13. And then you solve that on your calculator. That's calculator work 100% of the time. And your period is 61.2 minutes, because minutes are what we put in, minutes are what we get out. All right, let's turn the page. As per usual, these are story problems, and since I don't rewrite story problems, we'll just stick our note paper here. We're on page 24, and we are dealing with problem number 1. Let me see, I can write the formula over here. A equals A sub 0 times G to the power of T over P, right? I think that's everything. Okay, radioactive sample has a half-life, so we know our G is equal to 1/2, of 400 years. The period is equal to 4,000 years. How long will it take, so time is what we're looking for an initial sample, so my A sub 0 is equal to 80 pounds, to reduce to 5 pounds, so my A is equal to 5 pounds. All right, how long will it take? What is the time that that's going to take? So let's stick it into our formula. So my A is 5 equals my A sub 0, which is 80, times my 1/2 raised to the power of T, which we don't know, over 4,000. Crazy. This is going to annoy me. Anyway. Okay, I need to get this by itself, right? So we're going to divide both sides by 80. So, always forget. 5 divided by 80 is 0.0625. I'm not going to round as of yet because I want to keep my answers as pure as I can. So 0.0625 is equal to 1/2 raised to the power of T over 4,000. Now we're going to change this to log. So now I have the log of 0.0625 is equal to, and I'm going to just boop it right out front, t over 4,000 log of 0.5. Since we're dealing with decimals, I'm changing my 1/2 to a 0.5. Now, I need to get the t by itself. To do that, I'm going to have to multiply both sides by 4,000. Okay, I'm just doing this real slow. I mean, we could do it in one step, but I'm just going to go real slow with it so we can see this first one, because I don't think the examples really show you all of the steps. So we now have 4,000 times the log of 0.0625 equal to t times the log of 0.5. Now I want that t by itself, so now I'm going to divide by the log of 0.5. Okay, so those cancel, and I'm going to get my t. Now, all of this has to be put into the calculator. As I always suggest, parentheses, parentheses, parentheses. Make sure you're closing your parentheses. So I have 4,000 times the log of 0.0625, close the parenthesis for my log, and close the parenthesis for my multiplication. So I have this little parenthesis closed and that bigger parenthesis closed. Close your parentheses. Divided by log of 0.5, close that parenthesis, equals 16,000. 16,000 years is how long it's going to take, because remember we started with years, 4,000 years, 16,000 years, so that's a long time. That's how long it's going to take for this to go from 80 pounds to 5 pounds. All right? Okay, let's take a look at another one, number 2. For number 2, it says a strain of bacteria triples. So my growth rate is equal to 3. Every 2 hours, my period is equal to 2. If a culture begins with, so my A sub O is equal to 100 bacteria, how long will it be until there are, so how long, again, my time is what's missing. And my A, which is the final count, is 24,300. All right, let's fill it into our formula, right? I've got 24,300 is equal to 100 times 3 raised to the power of t over 3, right? Or sorry, t over 2. My period is 2 hours. Okay, since I'm dealing with time, I need to know the time we're working with. We're working with hours. So first step, dividing both sides by 100. I want to get my 3 raised to a power by itself. Okay, these cancel. This is dividing by 2 zeros, so I'm basically just taking 2 zeros away. So I have 243 is equal to, let's not waste space here, 3 to the t over 2. All right, again, we're going to logarithmic form. I'm going to boop my t over 2 out front. So I have the log of 243 is equal to t over 2 times the log of 3. Multiplying both sides by 2, right, because it's in the denominator, gives me 2 times the log of 243 equal to t times the log of 3. Right, these 2's cancel. Now I need to get t by itself, so I'm going to divide by the log of 3 on both sides. These cancel. T is equal to, calculator. I'm trying to make sure you guys can see. We have 2 times the log, where's my log button? Here it is, of 243. Close parenthesis for the log. Close the parenthesis for my multiplication here. Divided by the log of 3, close parenthesis, equals 10. 10 hours. In 10 hours, our bacteria will have tripled into 24,300. Okay? All right, we're chugging right along. Number 3. A 25-pound radioactive sample. So my A sub 0 is equal to 25 pounds. Is reduced to 2.5 pounds. So my A is equal to 2.5 pounds. After 5,000 years. The time, this time, is 5,000 years. What is the half-life? So my growth is 1/2. Rounded to the nearest 100 years. We don't know the period. So that's what we're solving for this time. Let's put in what we know. Put in what we know. My A is 2.5. My A sub 0 is 25. 1/10 of what it was. My G is 1/2. My growth. And it is raised to 5,000 over P. That's what we're looking at. We're going to divide both sides by 25 because we want the ratio part, the fractional part, to be by itself. Okay. Right there. 2.5 divided by 25 is 0.1, which is equal to, these cancel, 1/2, or 0.5 if you want, not 5,000 over P. Okay, we're going to set it up in logarithm and boop out front. So we have the log of 0.1 is equal to 5,000 over P times the log of 0.5. All right. Now my P is in the denominator this time, so that's what I'm going to be multiplying both sides by. Sometimes we have to move and shuffle our variable around. So now we have P times the log of 0.1 equal to 5,000 times the log of 0.5. To get P by itself, we're going to divide both sides by the log of 0.1. Okay, these cancel. Let's figure out what our period is here. I don't want to cover up the equation, but I need the lighting to be good. So let's try it here. So we have 5,000 times the log of 0.5, close parenthesis on my log, close parenthesis on my multiplication, divided by log of 0.1, close parenthesis, equals. So the period is, and they want it to the nearest 100 years. It's 1,505 years, but they want an approximation of 1,500 years. Chopping off a pretty decent amount of time, but hey, that's what they're asking for. Okay, so 1,500 years is how long it will take for that to lose 1/10 of its weight. Or I guess more than that, right? But there we go. So, as a recap, we are going to read the story problem and write down what they gave us. Okay? And then we're going to substitute all of that information into the formula. And then in this case, because all of these are missing either the period or the time, you are going to be using the logarithmic form. You're going to boop your exponent out front, and then you solve it just like a normal equation, right? You guys are good at this. You're doing fantastic. We're almost to the end of this year of math. You guys are doing great, all right? Go ahead and finish the rest of this lesson and meet me back here for lesson 8. Lesson 8 begins on page 26, and it's titled Changing a Repeating Decimal to its Rational Form. Basically, we know that repeating decimals are rational numbers, right? We learned that. We reviewed that. We've learned that many years ago, I would hope, but we reviewed that back in probably book 1. And so this is a way, this method is a way of changing that repeating decimal back to its fractional form, basically. So a change of repeating decimal back to its rational or fractional form requires an arithmetic multiplication or manipulation. I'm going to walk you through these steps as I go through example 1. So change the expression 0.2222222 forever and ever amen to its rational equivalent, to a fraction. So the first step is to let x represent the decimal. So x is equal to what they gave us, 0.2222222 forever and ever amen. Then the next step is we multiply both sides of that equation by a power of 10, which will bring the repeated decimal forward, okay? Repentant? That's kind of funny. Okay, so because this is just one number repeating consistently, we only need to multiply it by 10. So you have to multiply the whole equation. So you get 10x equals 2.22222 for an ever and ever amen. Now what we've created here is two equations, okay? And you're going to take equation 2 and subtract equation 1. Okay, so we're going to have 10x minus x, which is a 9x, and 2.2222222 minus 0.2222, which basically chops off that repeating decimal, right? It's chopped it right off. And now we just have a 2. So 9x equals 2. Divide both sides by 9. X equals 2.9. Now, if you put that in your calculator and divided 2 by 9, you would get 2.22222 forever and ever amen. But this is the fractional equivalent. It's rational expression. All right? So we took what they gave us and set up an equation. We multiplied that by a value of 10, or power of 10, that pulled the repeating part out from behind the decimal. And then we use those two equations we created to slice off, basically, the repeating decimals and then solve for x. All right, let's take a look at another example. Number 2. Change the expression 0.3636, blah, 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 on and on forever, amen, to its rational equivalent. All right, so x equals 0.3636 for on and on forever, amen. But this time, because our repeating is 2 numbers, we're going to have to multiply by 100. So 100x equals 36.3636, blah, 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 forever and ever, amen. You take equation 2, subtract equation 1. So 100x minus x equals 99x's. 36.36 minus 0.36 is 36. Divide both sides by 99, reduce because it's reducible, and it becomes 4/11. This is, okay? Now, way down here at the bottom, it says the repeating part does not always begin immediately after the decimal point, such as the number 0.0833333. The 3's are the repeating part. And so we have to modify our steps a little bit. So let's take a look at the top of page 27. Our steps are modified here, and we're going to go through those steps while we discuss example 3. So again, we're going to make an equation, x equals the repeating decimal expression. So in this case, we have 0.91666 equals x. Step 2, we're going to multiply both sides of the equation by the power of 10, which will bring the repeating part to the left of the decimal point. So remember, the 6's are what's repeating. So this time we have to multiply it by 1,000 to get those 6's here. Okay? Now, if we just stacked these two things on top of each other, though, we would still have a decimal because this part here isn't repeating. So we have to go one step farther, and we have to take our original equation again and multiply it by 100 so I can get the 6's lined up so that they cancel out. Right? Does that make sense? So when I go to subtract, so now I'm going to take equation 2 and subtract equation 3. So that 1,000 x's minus 100 gives me 900 x's. And 916.66666 minus 91.66666, my decimals cancel, and I'm left with 825. Divide by 900, reduce, we get 11/12. All right, so that one has one extra step because we're not just dealing with the repeating part right off the bat. We have some extra things. So we have to take an extra step. All right, let's take a look at these problems together. So we are in Algebra 2, Book 10, Lesson 8, page 27. Problems number 1 through 3 are here. It says convert the repeating decimals to their rational equivalents. All right, so for number 1, we have 0.111. On and on. I didn't draw the little dots, but these go on and on forever. Amen. So our first step is that x is going to equal 0.111, right? Now I need to multiply that by a power of 10 that gets this 1 over 1 point, and that's just going to be 10. So 10x is equal to now we moved it over, right? 1.111 repeating, okay? And now we subtract them from each other. I'm not going to rewrite all of that, but we're going to subtract this first part. So negative x plus 10 is 9x. Negative 0.1111 plus 1.11111 is just a 1. I'm solving for x by dividing both sides by 9, so x is equal to 1/9. All right, looking at number 2. For number 2, we have 0.0666. So my x is going to equal 0.0666, forever and ever, amen. We need to move 2 decimals, so I'm going to have to multiply by 100. So 100x is going to equal 6.66, Subtracting the first part from the second, I get negative x plus 100, or 99x's, is equal to negative 0. Oh no, we got to do one more step for this one. My bad. One more step. No subtracting yet. I got to get rid of that 0. Okay, so I'm actually going to have to multiply this by 10 as well. So I'm going to have 10x is equal to 0.666, forever and ever, amen. Forgot, we got one extra step this time. And I'm going to subtract that from my 100, okay? Now my decimals line up to completely cancel themselves out. So 100x minus 10x is 90x's, and 6.66666 minus 0.66666 is just a 6. Dividing both sides by 90, we get 6 over 90. They have a 3 in common, so it's going to be 2/30. This is my x, is the equivalent rational expression. Okay? Number 3, we have 0.0909090909, okay? So my x is going to be equal to 0.09090909, right? But to get this out, again, I need to multiply by 100. So 100x is going to be equal to 9.090909, repeating forever and ever, amen. So do my decimals cancel if I line them up now? They do, because it's 09090909, okay? So I can go ahead and subtract right away. So negative x plus 100x is 99x's, and then negative 0.0909 plus 9.0909 is just 9, all right? Dividing both sides by 99 gives us 9 over 99, which is 1 over 11, 1/11. All right, let's take a look at the next 3. For number 4, we have 0.13636. So the 36 is the repeating part. So that's the part we're ultimately going to be dealing with. But for now, x is equal to 0.13636, We have to multiply it by 10, 100, 1,000 to get that to come out. So 1,000x is equal to 136.3636, But Our decimals don't line up here. We have to take that extra step. So to get my decimal to line up, I need to multiply it by 10 to get the 3636 there. So 10x is equal to 1.3636 dot 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 forever and ever, amen. Now our decimals line up, so we can subtract this one from the 1000 one. So 1000x minus 10x is 990 x's, right? 136.363636 minus 1.363636 is 135, okay? Divide both sides by 990. Definitely 5 goes into this, so let's see. I'm sure it's probably more than 5, but let's just take a look. Let's see, 5 goes into this 25 times, right? It goes near 2, nope, 27 times, all right? Check your math. Goes in near 2, carry the 35, 7, okay. And 5 goes into 999. It goes into 9 once. It goes into 49 9 times. And it goes into 10 twice. Right? 192. Let me double check. 5, 4, that makes that a 49, which is, that makes this, oh, it's not a 10. Jeez, that's a 40, so this is an 8. All right, that makes more sense. So 27 over 198. The only way that this will work is if 3 goes into 198. Let's see, it would be 6. Oh, it does. Look at that. Let me get my calculator out just to make sure I'm getting this math right. So I have 135. 135 is where I started, and I divided by 5, which gave me 27. Divided by 3 is 9. This probably reduces farther than that, but let's see. I had 990 divided by 5, which gave me 198. Divided by 3 is 66. Oh, it does go further, okay? So then I have 3 over 22, right? Because 3 goes into 9 3 times. 3 goes into 66 22 times. That is as far as it goes. Sometimes when we're doing things manually, it takes a little bit longer. But 3/22 is the reduced form for that, okay? That's number 4. So number 5. We are at 0.666 dot, 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 dot. I mean, this is almost exactly the same as number 2, so I'm not sure what we're going for here, but x is equal to 0.666 dot, dot, dot. We have to multiply it by 10 to get that repeating number out. So 10x is equal to 6.666 dot, dot, dot. We could subtract this first one from the second. Negative x plus 10x is 9x's. Negative 0.66666 plus 6.6 is 6. Okay, so x is equal to 6/9 or 2/3. Okay, 2/3. Final one. This one's a little bit more complicated, but nothing we can't handle. It's kind of similar to number 4. 0.08333. The 3's are the repeating part. Our original equation is going to be x is equal to 0.08333. We need to multiply it by 10, 100, 1,000 to get that 3 out. Okay, so I have 1,000x is equal to 83.333. Okay, now I can't just subtract this because the decimals don't line up, right? I have to multiply again, and this time by 10, 100. Because I need it to be a 333, I don't have to go farther than necessary. So 100x is going to be equal to 8.333, forever and ever, amen, right? And now I can subtract this one. So 1,000 minus 100 is 900x's. 83.33333 minus 8.33333 is 75, right? The decimals cancel each other off, okay? And 83 minus 8 is 75. So x is going to be equal to 75 over 900. Now, I know 25 goes into each of these, so It's going to be a 3 over what? 900 divided by 25 is 36. Oh, again, it's going to be equal to 1/12. Okay? 1/12 is the reduced ratio, or the rational equivalent of 0.08333333. Okay? So the process remains the same, even though some of them have an extra one. We're going to set and make an equation of x equals our original repeating decimal. We are going to multiply that repeating decimal by a value of 10, or a multiple of 10, where we can get the repetition outside of the decimal, right? And then we are either going to subtract the original, or we might need to multiply the original by another multiple of 10 so that the decimal portions line up. Okay? Here, the decimal portions lined up right away. We didn't have to multiply again, but this one we did. The decimals should cancel each other out completely. And then you're left with a simple equation. Solve for x, reduce your fractions, reduce, reduce, reduce. You don't want to lose points for not reducing. Look how long this one took me to reduce. But I got there, okay? Reduce your fractions. All right, that's it for lesson 8. Go ahead and finish the review. Meet me back here for lesson 9. Lesson 9 begins on page 29, and it's another part 2. Yay! The law of signs and the ambiguous case, part 2. Part 2. So remember, in part 1, if the given side angle data for the triangle indicated 2 possible triangles, right here, right? RA less than B, RA greater than H was 2 possible triangles. Then use the given data and the law of signs as done previously to solve the first triangle. Then for the second triangle, we're going to exchange angle B, which you just found, okay, of the first with its supplement. Right? So if it's 30-degree angle, the supplement of that is 150 degrees. And then you solve it again. Because supplementary angles have the same sine value. The angle of 30 degrees, or the sine of 30 degrees and the sine of 150 degrees is the same. Okay, so they have the same sine value, and this is the reason that side angle data can yield 2 triangles, right? So I know that's what you guys were all wondering when we learned this last time. And finally, you've got the information. So we can move forward. Example 1. Solve the triangle given the angle A is 35 degrees, B is 18, side B, and side A is 12. All right, so I'm going to slide us up here so we can get the whole thing, because the whole rest of this page is this example. So it says determine the height of the triangle, and they do that here. The height is 10.3. Okay, A is less than B. A is greater than the height. So less than B, greater than the height. There are 2 triangles, right? So they're using the law of signs and determine that angle B is 59.4 degrees. If angle B is 59.4 degrees, then angle C is 85.6 degrees. And side C is, they wrote a degree, it threw me off for a second here. Side C is then calculated to be 20.9. That is triangle 1, right? But now we need to go back basically to this step, or maybe, I guess perhaps this step, okay? And instead of having 59.4, we need to find the supplement, which is 120.6, and we're going to put that in. So if my angle is actually, angle B is 120.6, then angle C is 24.4. If angle C is 24.4, they keep putting a degree and it keeps throwing me off. Then side C is 8.6 units, whatever the measurement is. Okay, and so they kind of have it drawn here, what it would look like. This being angle B way over here. It'd be lined up here with the side C, but angle B could either be that, 120.6, or it could be 59.4. That's basically what this represents. Okay, so if we get to the 2 triangle part, you know, if this works out in a 2 triangle way, we just have to do it twice because there are 2 possible triangles. All right, let's turn the page. Turning the page brought us to the problems for us to work on together. We are in Algebra 2, Book 10, Lesson 9, page 30. I didn't write the whole law of sine thing up here, but I did write the equation for H. Problem number 1, the instructions say find the missing measures of every triangle that exist for each set of data. Okay, so for problem number 1, we are solving for angle B, angle C, and side C. Okay, we are given that angle A is 36 degrees, that B is equal to 8, and A is equal to 6. Now, I'm going back and looking at my little triangle here, my little gray box. My A is less than B, so now I need to know is what my A is compared to my height. So we need to solve for the height, which I wrote down here. So the height is going to equal B, which is 8, times the sine of 36 degrees. Okay, calculator, work. So I have 8 times the sine of 36 degrees, closing my parentheses for the sine, closing my parentheses for the multiplication, gives me my height is equal to 4.7. So A is less than B, but A is greater than the height, so there are 2 triangles. So we need to solve for both. I'm not going to set up a second set of BCCs. We're just going to put a comma, and we'll do it that way. So I have the sine of 36 degrees, which is angle A, over 6 is equal to the sine of angle B over 8. Okay, this is the law of sines. To solve this as a proportion, we're going to cross multiply. So 6 times the sine of B is going to be equal to 8 times the sine of 36 degrees. I'm going to divide both sides by 6. The sine of B is equal to 8 times the sine of 36 divided by 6. Okay, so I have 8 times the sine of 36. Close the sine, close the multiplication parentheses, divided by 6 equals. So it's 0.7837. That doesn't really help us at all. We need to find out the inverse, right? So on mine, it's right underneath the sine button. So I'm going to hit Shift, sine button, gives me the negative. I'm going to stick the answer in, close the parentheses, hit equals. B is equal to, I'm going to just have 51.6 degrees. Okay, it's 0.60. I'm just going to lop it off. B is 51.6 degrees. Okay, so what is C? Well, C is 180 minus that 51.6 minus A, which is 36. So 180 minus 51.6 minus 36 equals 92.4 for my C. Okay, and now I need to find the side C. To do that, I have to use the law of sines. So sine of 36, which is my angle A, over side A, which is 6, is equal to the sine of 92.4 over side C. So I'm going to have C times the sine of 36 is equal to 6 times the sine of 92.4. Dividing both sides by the sine of 36. And we will find our C. Okay? I definitely don't have enough room to do all of this on this piece of scratch paper. We're going to have to get a different one. So, calculator. We have 6 times the sine of 92.4, close the sine, close the multiplication, divided by the sine of 36, close the parentheses, equals 10.198, blah, blah, blah. So I'm going to say 10.2. 10.2. That is one set of the triangle. we still have to find the other set of the triangle, okay? So we use 51.6. We need to find the supplement. What if B is 180, oops, minus 51.6? So B could also be 128.4 degrees. So now we need to find all of the information for C from that. So 180 minus 128.4 minus 36 gives me what? Maybe I'll squish it in here. 180 minus 128.4 minus 36 tells me that C is 15.6 degrees in this particular triangle. Now we need to find part C again, side C. So I'm going to have the sine of 36 divided by 6 equal to the sine of 15.6 divided by C. Cross multiplying tells me C times the sine of 36 degrees is equal to 6 times the sine of 15.6. Dividing both sides by the sine of 36 gives me my new C. Again, calculator work, close your parentheses. 6 times the sine of 15.6, close for the sine, close for the multiplication, divided by the sine of 36, close those parentheses, equals 2.7. Okay, so you can just write it like this. I can, separate them with a line is what I did. This is what one triangle would be. That is what the other triangle will be. So I decided to give myself some extra room. So let's take a look at number 2. For number 2, we are given that A is equal to 64 degrees. Side B is 112, and side A is 108. So we are solving for angle B, angle C, and side C. All right. First thing we need to do is look at A and B. A is less than B, so we need to solve for the height. The height is going to equal 112 times the sine of 64 degrees. So I have 112 times the sine of 64 degrees, close my parentheses, gives me 100.7 basically. So A is less than B, but A is greater than H. So there are two triangles that we need to solve for. Let's start. We are going to start for angle B because that's the only other information we were given. So the sine of A, which is 64 degrees, divided by side A, which is 108, is going to be equal to the sine of angle B divided by side B, which is 112. Now we're going to cross multiply. The sine of angle B is equal to, times 108, and I wrote that weird, I apologize, is going to be equal to 112 times the sine of 64 degrees. We're going to divide both sides by 108, and we get the sine of B. Okay, calculator. We have 112 times the sine of 64 degrees, close parenthesis for the sine, close parenthesis for the multiplication, divided by 108 equals, it's a decimal, 0.9321, blah, blah, blah. Basically, if we round it, I'm not going to round yet. Remember, we need to find the inverse because we're looking for angle B. So my inverse sign is underneath my sign button. So I'm going to hit Shift, Sign. So sign to the -1, that's the inverse. I'm going to put the answer in there because calculators are fabulous that way. Close my parentheses, equals 68.8 degrees. So B is 68.8 degrees. Now I can find angle C because 180 minus that 68.8 minus A, which is 64, will give me C. So 180 minus 68.8 minus 64 equals 47.2. 47.2 degrees. Now I can solve for side C. Okay, and side C, we're going to use this part again because that was the original most amount of data we were given. So the sine of 64 over 108 is equal to the sine of 47.2, we just calculated, over side C. Cross multiplying, we get that C times the sine of 64 is going to be equal to 108 times the sine of 47.2. Dividing both sides by the sine of 64. Okay, cancels, gives me my C. So calculator, clear, 108 times the sine of 47.2, close, divided by the sine of 64, close, equals 88.2, right? We're rounding 1 based on a 6. So 88.2. But remember, there's two triangles here. B can be 68.8, but it can also be the supplement of that. So now we need to take 180 minus 68.8. So B could also be 111.2 degrees. Where does that leave C? Well, we've got to figure it all out again. 180 minus 111.2 minus the 64, which is our A originally, minus 111.2 minus 64 equals 4.8. Is that really it? 180 minus 111.2 minus 64 equals, wow, 4.8. That is a tiny angle, okay? 4.8 degrees could be C. I guess that's not unheard of, but it's a very small angle. So now we need to go back to this step, and instead of 47.2, we're going to put in 4.8. So I'm just going to start my notes right there. So sine of 64 over 108 is equal to the sine of 4.8 over C, because now we need to solve for the other side of C, right? So C times the sine of 64 is going to be equal to 108 times the sine of 4.8, dividing both sides by the sine of 64. Okay, it gives me C is equal to, pull out my calculator, 108 times the sine of 4.8, close, divided by the sine of 64, close, equals, C is 10.1, right? I've got a 0, rounding it based on a 5, 10.1. So those are the two triangles, with one with this measurements, with these, the other with all of those measurements, okay? And that's what we're trying to accomplish here today. So let's take a look at number 3. For number 3, we are given that A is equal to 35 degrees and B is equal to 17. Side A is equal to 7. A is less than 17, but what about the heights? But I'm going to set up my, we're looking for B, angle B, we're looking for angle C and side C. So my height is going to be equal to 17 times the sine of, oh my goodness, times, close my parenthesis too early, times the sine of 35 degrees. So calculator, I have 17 times the sine, oh, I don't like that, 17 times the sine of 35 degrees. Okay, make sure you're closing your parentheses. I'll try and put this in a useful place. Is equal to 9.75, so I'm going to say 9.8. Now, A is less than our H. So if we think back to our little box, A is less than B, but A is also less than H. So there are 0 triangles that this would even make. Remember, our side A cannot be less than the height. It can be equal to the height, but this triangle looks like this. The piece doesn't go far enough to reach the other side. Okay, so there are no triangles. That's great. Number 3, we're done. All right. Make sure you're checking with that little box. That little box is our friend and helps us to not do work that we don't need to do. Okay. That's it for lesson 9. Finish the review. Lesson 10 is a quiz. And as always, if you have any questions or you need help with a specific problem, do not hesitate to contact me. Otherwise, until next time.